Hi everyone, it's Mr. Kennard again. It's investigation 4, the second part of it. Last lesson, Mrs. Mott took you through gas expansions and contractions, looked at a balloon on a water bottle, putting that into hot water and cold water and see how it affected the particles of gases. In this investigation, part of the investigation, we're going to look at liquids. Can the same thing happen to a liquid? So let's review a little bit from Mrs. Mott's investigation. All right, so let's review a little bit about our previous lesson with regard to taking that air and putting it into a smaller space or a bigger space. Why could we push air into a smaller space? Well, the biggest reason was there was spacing between the particles. Spacing between the particles of gas. They're spread apart, therefore they have lots of room, and then therefore they can be pushed together. The particles can be pushed together because they have some room between them. Number 2, what do we call it when we make the volume smaller because of pressure? The answer is right there in the word pressure. It is compression. Compression. In the word compression is the word press. You're pressing them together, you're forcing them together, the press. Now, in the last activity, they made a volume of gas smaller, but we didn't put pressure on it. Do you remember that one? What did we do to make the volume of gas smaller in that instance? Instead of pushing the particles together, we actually did something different with them. We actually cooled the sample. We took it and we put that, we put the water bottle with the balloon on the top of it into some cold water, and as a result, the gas particles didn't hit each other as often, and so the particles could move closer together. And as a result, they fell out of the balloon and back into the bottle. So if we didn't push those particles back in, they went in there on their own. What is the name for the energy in moving particles? If you'll remember that, I like it because it starts with my same initials. K. Kinetic. Kinetic energy is the energy of moving particles, of motion. And what we're going to find out is that motion, that movement, that kinetic energy comes from either changing or heating it or cooling it, changing the heat. So what do we call it when we make the volume smaller because of reduced kinetic energy? That is called contraction. And that one is getting smaller because we are cooling it off, or reducing the kinetic energy, or reducing the amount of movement energy that is in there. So moving forward, that was all with gases. We heated them up, we put it in hot water, the balloon expanded because the particles got kinetic energy and moved faster and farther apart. When we put them in the cold water, they slowed down, got less kinetic energy, was taken away from them, and they fell back into the bottle. The next question is, well, could that still apply to a sample of a liquid? So that becomes our focus question for this part of the investigation. What happens to particles in a sample of liquid when the liquid is heated and cooled? Maybe the same things, maybe not. We'll find out. And that leads us to the next question. Can I change the volume? Remember, volume is how much space it takes up of a liquid in the syringe by doing the same things we did with the syringe filled with air. If you'll remember, the syringe with the air, we pushed on the plunger and we pulled on the plunger. Can we do the same things with a liquid to change its volume? Air, remember, has lots of space, so it can be compressed and it can be expanded. And because of those, but liquids, I don't know. Are they the same or are they different? We're going to find out. What you just saw in that video shows that you cannot compress a liquid. They were able to do that with the syringe with the air in it. You could press it in and it would spring back, or you could pull it out and it would spring back to where it was. But even though they were trying to press on it or pull on it, the water wouldn't let them do that. The liquid would not let them compress it any farther. And same thing with pulling it out. There's no room for that plunger to move. Why is that? Well, let's look at some 3 samples of matter. I pulled this from the ebooks on particles, and you can see over here there are the 3 samples of matter. We have a solid, we have liquid, and we have a gas. So if they're in one of these vials, you can see how they take up the space within those containers. Solids very rigid, liquids kind of just at the bottom, and then gases are all spread out. So when you apply force to it, like you see here, that plunger in there, what's happening? Are we able to do that with the solid? No, because they're already packed in there so tight, there's no space for them. Can they do it with a liquid? Nope. Again, they are touching each other, and once that space is reduced, they can't change into any other space. But over here in the gas, you see, there was lots of room to be able to compress them and squish them closer together. As a result, you can compress a gas, but not liquids or solids. So from that previous video, we learned that we cannot compress water any closer. They're already packed in there. You can compress the air, but you can't compress the water. So the other term we used was to contract the air, meaning making it smaller by, in this case, by changing the heating or cooling of it. Can we do the same things with water? We're going to find out. We have a little experiment or demonstration to show you. Here on the page you will see the procedures for everything. Glass bottles, rubber stoppers, clear pipes. And what you'll make is, or the video will show you that we have some blue water put in there, and we've raised it up to a certain level on that little card stick. And then the procedures, once we do that, we will place the bottle into cold water, and after the 3 minutes, we'll then label where the C was for cold, and then move the bottle to a warm water. In 5 minutes, they will label it to the water level H. So watch, and the following video will show you what takes place. Now that we've seen the video, I want you to go back to the instructions part of this lesson and upload this heating and cooling water sheet, because you're going to complete this and upload it to Canvas. What you saw, what we have here, is the questions about what happened when you place the bottle system in the cold water and then again in the hot water. You'll need to draw on the actual card there stuck to the tube in the stopper where those levels were at, and then explain what happened to the blue water in those cases. And then there's two more questions there at the bottom, 3 and 4. We don't have to worry about number 5. We'll answer that one a little bit later. All right, so go ahead and do that now and get that submitted up into Canvas. And if you need to, go back and watch a little bit of the video. So now that we've seen two different ways to kind of manipulate water in a volume of a liquid, let's go back and have some sense-making discussion. Were we able to reduce the volume of the water in the syringe by pushing on it? And the answer with that was no. That's the whole principle behind hydraulics. If you've ever heard of hydraulics, a hydraulic car lift, a hydraulic press, a hydraulic this, you're able to, because water cannot be compressed anymore, you can put a small little pressure on one end and it will raise a larger body or weight on the other end. Number 2, were you able to increase this time the volume of the water in the syringe by pulling on it? And again, no. It was in a trapped system. It couldn't expand any further. It couldn't get larger in volume. So the answer for that one is no. So how was the behavior of the water in the syringe then different from the behavior of the water in the air in the syringe? How was the water different than the air? Well, obviously you couldn't do the same things. Almost completely opposite. You could compress air, but you could not compress the water. You could expand the air, but you couldn't expand the water. Why do we think that water can't be compressed? Again, it goes back to our earlier thing. It's about the spacing of the particles. Spacing of the particles that take place. Review a little bit more. What happened to the volume of air when we heated it? When you put that bottle and balloon system into the hot water, it expanded. The particles moved further and farther apart. They moved faster. They needed space to move. They had a lot more kinetic energy. What caused the air to expand? What's it's caused? The heat, or kinetic energy. Kinetic energy, the motion, and that is brought on by heat. So what happened when the volume of air again was put into the cold water? It contracted. And what happens with a contraction is they get closer together, not by force, but by changes to the kinetic energy, so cooling it. What about when we placed our bottle system? In this case, the bottle system with the blue water in it. What happens when we put that in the cold water? Well, what we saw was the water actually went down into the tube, went downward into the tube. Why? It was being contracted. It was getting closer together, and gravity's going to pull on that and pull it back down the tube. What happened when we placed the bottle system again now in hot water? The water went up the tube. Why? It was expanding. It needed more. It was giving more heat. That was giving it more kinetic energy. They bumped into each other. They needed more room to expand. Can't trap them in a classroom. You need to let them out on a gymnasium or on the football field and let them run around. So what is it that we said caused the water level in the pipe to change when we put the bottle into the cold water? Obviously, it was the cold, the reducing kinetic energy. Kinetic. Can't write today. When you reduce it, you cool it off, and therefore the particles get closer together. Last couple ones here. What caused the water level in the pipe to change when we put it into the hot water? Again, instead of reducing the kinetic, you're increasing kinetic energy. How are you doing that? You're adding heat. When you add heat, you're causing it to move faster and farther apart. They move faster, they farther apart, they spread out, they need more room as a result. And finally, describe what you think happened to the particles in the bottle system when it was placed in the hot water. If you were just listening, that's just what I said. You have to work with kinetic energy and expansion. You increased the kinetic energy, and that led to expansion. And we saw that with the liquids in our little bottle system. There's always somebody in the room who wants to say, what if you turn it upside down? What's going to happen then? Well, let's try that. What do you think will happen if I turn this bottle upside down? If I surround the bottle, will it fall out first of all? And go back to that. Is it going to fall out? Is the water going to drain out? Probably not. Number two, if I surround the bottle with a hot cloth, what's going to happen to the water level in the clear pipe? Will it move up towards the bottle in this case, because it's upside down? Or will it move down towards the end of the pipe with the hot water or the hot cloth? Well, I have a little video to show you. So watch this, and then we'll discuss it on the backside. Well, just as suspected, what caused the water in the pipe to go down, in this case away from the bottle? Again, heat. It was a hot cloth they were working with, and that hot cloth caused them to expand. When the volume of water expands, what is getting bigger? That's always a good question. Is the distance between the particles increasing, or is it the size of the particles that's increasing? What do you think? Do the particles get bigger because they have more energy? What about you? When you eat food, when you eat candy after Halloween, did you all of a sudden get noticeably bigger by eating the candy because you had all this energy? Or you just needed more space with your friends to run around in? So probably. Yeah, it is the distance in this case. The distance gets bigger. They bump into each other. You need more space. You need more room. So again, what causes this increase in distance between the particles? Heat and kinetic energy. It's the heat. It's energy. The particles, when they have heat, they move faster. They move farther apart. They need more room. They bump into each other. They need more space. They expand. All of that goes together. As we saw earlier, yes, gas particles, as we know from before, are flying around with large spaces between them. So you got a particle here and a particle here and a particle there 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 and a particle, and they're bouncing all over the place, going this direction, that direction, this direction, that direction, bumping in all over the way, going here, going there. Oh my gosh, it's like crazed maniacs at recess back when you were in second grade, running and running and running because you couldn't do anything. Actually, some of you probably will do that now if we gave you that out in the yard in the front. So yeah, it's about the spacing. And again, what causes that? Heat. Now, you may not think about this. The particles actually in the water are also always moving. Always moving. They move around each other. They vibrate, kind of a rapid back and forth motion. Gravity's pulling them all down, keeping them is close together. But as we saw in that other one, they're all kind of, if you've got them at the bottom of the container, you've got them all packed in there a little tight, and they may move around a little bit here and there, but they're packed within just the bottom of that container and swishing around. If you turn the container, it flows out. You can do that with water and most every other liquid as well. And what we found out from this today is water, just like air, expands when the particles are pushed farther apart, and the kinetic energy of the particles increases. They move apart, they spread out, they expand. So hot water actually takes up more volume than cold water. It's an interesting phenomenon that here, when it's cold, things float a little bit easier than if it's hot water. It's less dense. There's always somebody who says that that little bottle system looks like a thermometer. It works like a thermometer. Well, how do you think a real thermometer works? What happens when you put the thermometer into the cup of hot water? Particles do what? Expand. And that causes them to go up the tube for a higher temperature. Cool? All right. We're going to try a little bit more, look at this a little bit more with some water a little bit later on. All right? Check for investigation 4.2B next. Thanks, everybody.